In our last lecture, we worked to find the equilibrium concentrations of H2L+, HL, and L- for a 0.0500 molar solution of H2L+, which is our shorthand notation for a fully protonated leucine molecule. In this lecture, we're going to investigate the equilibrium concentrations of the fully deprotonated leucine molecule, L-. Since L- is the fully deprotonated form of our amino acid, we need to recognize that L- is the most basic form of the amino acid, and we'll use the value of Kb1 to solve for the equilibrium concentrations. We'll tackle the addition of the second proton in a separate ice table. For now, I've filled out our first ice table and used the law of mass action to write the equilibrium expression. Plugging our values into the Kb1 equilibrium expression, we see that we can make the x is small approximation because our initial concentration is at least 10 to the third larger than our K value. Solving for x gives us the concentration of hydroxide ion present. Recall this is a basic reaction, so we can solve for the POH and the pH quickly. We can plug our values of x into the ice table to get real data in our second equilibrium line, which means that the only concentration we're missing now is for H2L+. To solve for this missing concentration, let's consider the second basic reaction of leucine where HL will react with water to form H2L+. We'll need to bring the concentrations of leucine and hydroxide along with us to do this. Here we've got our initial concentrations filled in from the last ice table. We've noted the change and the equilibrium expressions, which we've dropped into Kb2. A quick inspection of this expression reveals that, again, we have the ability to say x is small because 10 to the negative third concentrations are much larger than our 10 to the negative 12th K value. We see that once the x values are canceled out, it leaves x times the concentration over the concentration, which simplifies to just x equals our Kb2 value. Are you starting to see a pattern here? Filling in our IC table, we can then organize all of the data into a single table as I've shown here at right. With that, we've tackled the composition and pH of the most acidic form of leucine, H2L+, and the most basic form of leucine, L-. We've left out the pH and composition of HL, which is the most challenging calculation. We'll save that for the last lecture in the series.